So the first thing we're going to look at, of course, is the parent function. So you see that this parent function, f of x is equal to 1 over x. The defining feature of a rational function is that there is x in the denominator. Now, a rational function could also have x in the numerator. It's still a rational function, but what makes it rational is x in the bottom, all right? So it says a rational function is a function that can be written as a ratio of two polynomials. Its graph is called a, ooh, don't look. What is the graph of a rational function? Well, you probably already saw, right? Yeah. Yeah, the graph of a rational function is called a hyperbola. It's a hyperbola, which has two separate branches, like you see in this parent function here. Now, what is special about a hyperbola that we haven't gone over yet this year? It does look weird. What makes it look weird?
Because they're not like, it's not like one singular like line you go about.
Okay, there's two parts. Yeah. Do you know what makes this shape? There's something starting with an A. There's actually two things on this graph starting with an A. Oh, someone got it last class. Do you guys know? What? Not quite. AS. Yes. There are two asymptotes. There are two asymptotes. Does anyone know what an asymptote is? Yes, perfect. Okay, so let me draw the asymptotes here for you. Now, asymptotes are normally drawn with dotted lines. So there is an asymptote here. And there is also an asymptote here. What is special about these asymptotes? What does the graph not do? It never touches them. That is what makes an asymptote an asymptote. It's the graph continuously approaches the line, approaches the asymptote, but never actually touches it. Yeah, it infinitely gets closer and closer and closer. So at some point, it's 0.000000001 away from the line, and it gets even closer, but it never actually touches it. That is what an asymptote is. So here, this line that is vertical, what is the equation for that asymptote? X equals 0. So one of our asymptotes is at x equals 0. What about the horizontal one? Y is equal to 0. So looking at this, what is our domain for this function? So let's think about this. What is our lowest, our least x value? I'm going to the left. When do I stop?
You don't.
I never do. So what's my least? Negative infinity. Never touching, so it's a parenthesis. And then where do I stop? What do I not touch? 0. So I have to stop at 0. And should this be a bracket or parenthesis? Parenthesis. Now, do I just stop at 0 or is there more to this graph? Oh, I need to now start at what?
0.
I start at the boundary of 0. Yeah, I'm not touching 0. So I put a parenthesis. And then I continue to the right. How much? Infinity. Good. And yes, guess what? It's the same for the range. Will the domain and range change? What happens if I shift this graph left 2? Is my asymptote going to move? Yes. So if I shift it left 2, right? I'm shifting it left 2. My asymptote is now over 2. So my domain is going to change. So yes, the domain and range will definitely change here. All right. So when you are trying to graph a rational function, one of the major aspects that helps you graph it is the center where the two asymptotes meet, right? So where is the center of our graph here for the parent function? Where's the center? Where the two asymptotes meet. It's at 0, 0, yeah, for sure. So here our center is at 0, 0. So that's a characteristic of the parent function. And also, does this function have a stretch or compress? The parent function. Is it stretched or compressed? The original, nothing's happened to it yet. Is it stretched or compressed? No. No. The parent function is as plain as it can get. Nothing has happened to it, right? So, again, just like all of our other functions, the first perfect point should be where? 0, 0, and then where do you go from 0, 0 to plot the next point? Yeah, you go up 1 over 1. So same thing here. I know that this graph is kind of weird. It goes up by 2. So to go up 1 over 1 is here. And then over 1 down 1. So that's how you would graph the parent function. You graph the center of the asymptotes, and then you graph up 1 over 1 down 1. And then you kind of just sketch the rest of the graph. None of the other points really matter too much. Okay? All right, so now let's take a look at transformations. This is just like any other function that we've gone over. We still have the same a, h, and k. Now, what does a tell us about the function? Without reading, in your own words, what does a tell us? Vertical slope, right? The vertical stretch or compress. If that number is bigger than 1, what's happening? It's a stretch. If it's less than 1, it's a compression. Good. What about h? What does h do to the function? Yes, it means it moves where? Left and right. Good. If h is negative, what does that mean? Goes to the right, right? And if h is, what did I just say? If h is positive, where does it go? To the left. What about k? What does that do? Up or down. Wonderful. So, do you need me to do an example? I don't think you do. Go ahead and do a and b here. And then also do a and b on the bottom. So do those 4 problems. Okay. So, Alyssa, could you tell me what transformations you got for A?
I said that it was horizontally translated right 8 and up by 5.
Good. So it's translated right 8, which this tells us the right 8 right there, and up 5. What about B? Hold on. Matt C.
Vertical reflection, vertical stretch by 3, and translation down.
Beautiful. Vertical reflection right here. It's vertically stretched by 3 and translated down 2. What about A? Amada. Up 4, good. Beautiful. Vertically stretched by 2 and vertically reflected. Does this function move left or right at all? No, right? It doesn't have anything after the x. And what about B? Michael M.
Translated 4 right and then 2 up.
Awesome. Translated 4 to the right and 2 up. Any questions on transformations? Right, pretty straightforward. We've dealt with transformations many, many times. Okay, so now let's go a little bit more in depth with domain and range. So looking at this function right here, 1 over x plus 3, and then minus 5. Has the domain changed from the parent function? Yes, why? Very good. The asymptotes have been moved. How much? Where are they moving? Where is this function moving? Good. Down 5 and 3 to the left. Good. So our asymptotes are actually where? At x equals -3. Because remember, it moved to the left 3, so it's at -3. And y equals -5. Good. And let's look at this a little bit. Why do you think, or why does it make sense that in this problem we can never have x equals -3?
Because it never actively touches.
Right, but why doesn't it? So look at our function. Why can x never be -3? Think about what you know about fractions. Why can x never be -3?
Can't divide by negative.
Oh, can't divide by. If x is -3, what is the denominator? If x is -3? 0. Can you divide by 0?
No.
No, it's undefined. So that's what's creating this asymptote here. You can never divide by 0. So that's why there's an asymptote at x equals -3. So basically, you can determine your x asymptote by looking at what is going to make this denominator 0. Oh, -3 is going to make it 0, so x cannot be -3. That's our asymptote. Okay, so now our asymptotes tell us what our domain and range is going to be. So let's try domain in set notation because it's actually easier. X is an element of all real numbers such that, what can x not be? What is the only thing x cannot be?
-5.
So x cannot be -3, and we're done. Anyone want to take a stab at what the range is going to be in set notation?
The same thing, except it can't be positive.
It can't be -5. You're right. -5. Is this making sense? Okay.
Asymptote is just when it can't.
Right. Asymptote is a line on the graph that your function never touches. So your x value can never be that vertical asymptote, and your y value can never be that horizontal asymptote.
Okay.
They just determine what the values cannot be. Good. Okay, so I think that you guys can do the rest just fine. Go ahead and find the equation in this next example, and then do A and B on the bottom. Oh, what equation did you get for this example, Chris? Oh, that's okay. Here, we'll pick another. Connor, what equation did you get? OMG. Becky,
1 over x minus 1 minus
Beautiful, yes. So look, we're trying to first figure out where our asymptotes are, right? So I'm going to pick a line that is directly in the center of my two parts of my graph. So here we have an asymptote, and also here we have an asymptote. So all we really care about right now is where did the center of my asymptotes move from 0, 0? So it moved to the left 1. Again, this is numbered by 2, so we have to remember this is just left 1, and then we move down 2.
So wait. Then wouldn't it be plus 1?
Yes,
X plus 1?
you're right. Plus 1. Left 1, down 2. And then did it stretch or compress at all? No, right? Our perfect points on our graph are just up 1, over 1. Over 1, down 1. That's perfect. Any questions from this graph? All right, so over here, what did you get for A, Allison?
Domain and right?
Yes, yes. What'd you get for the domain first?
Double squiggly
Yeah.
X. And I zero number.
Uh-huh.
Dot X equals 0.
Is not equal to 0. Good. And we'll pick another person for range. Dane? Where is he?
Y. Y is not equal.
Perfect. And therefore our asymptotes are where, Austin? Where are our asymptotes? Where are our asymptotes?
Oh, 0 and 4.
Ah, x is equal to 0 and y is equal to 4. Those are our asymptotes. Good. Okay, what about part B, the domain? Haley?
The domain
Yes.
would be squiggle bracket. X is the little e thing. All real numbers.
You guys can just say in. X is in all real numbers, okay? X is in all real numbers. And then,
Such that x does not equal -4.
beautiful. And what about the range?
Oh wait, no, not -4, positive.
Ah, yes, positive 4. Good. And what about the range, Ashley S?
The squiggly thing,
Mm-hmm.
y and all numbers.
Good.
And then the line,
Yeah, such that.
such that, and then y is not equal to.
Beautiful. And our asymptotes are where, Zaria? Beautiful. Any questions?
Why is the 2 not negative?
Because it's normal, remember?
No.
Only the x's is normal, opposite. Okay.